Hello, so it's going to be a bit of a shorter lecture today because of the test. And this is where I believe we left off. We were talking about mill-equivalent bar graphs. So this was a way to represent water analysis, ion analysis, to separate the cations and anions and give the mill equivalents of each of them in an easy to interpret fashion. So one thing that you can do very easily from a mill equivalent bar graph is actually figure out something called hypothetical ion combinations. So what this means is if I were to take that water sample and dry it down, I could very easily look and figure out what type of compounds would be in the water. So for example, you can see in the examples below, we could have calcium bicarbonate, but calcium can also combine with sulfate and the chloride. So for example, on a test, I may ask you what all the calcium compounds are going to be. So you combine it with calcium bicarbonate. So we can write that out, calcium, and then bicarbonate. There's going to be two of them. Remember, calcium has a valence of 2. Calcium sulfate, and then calcium chloride. So that might be a test type of question, is to ask you what hypothetical combinations you might have. I know I have another example coming up in a minute. So something else that's important to know is whether your ions balance out. And we talked about this, I think it was last week, in that sometimes the analysis is not perfect. There are a number of reasons for this. Sometimes there's just a certain amount of error in the test, whether it's human error or the testing error. Sometimes there are other compounds that have not been tested for. So for example, iron is a positively charged ion, and maybe the analysis didn't include iron, and maybe there's enough iron to make the cations not balance with the anions. Sometimes there's something else that might be in the water that actually reacts with the test, whether it's pH or sediments and silt and things like that. And sometimes these tests can be relatively finicky. So this is the formula. Basically, you're subtracting the anions from the cations, and you're dividing by the total amount of mill equivalents times 100. And I'm not sure where I got this number from, 10%. Maybe wastewater. I know it seems a little high, but that's, and I can't quite remember where I got the water from, but it's going to depend on the type of analysis you're looking for. If you're looking for something like drinking water, then the error, you're going to want it to be that a lot smaller, and there would be standards on that. So I'll show you an example of this in a minute, and we'll make another one of those mill equivalent bar graphs. So this is what a question might look like on a test. It'll have some water analysis, and then it's going to ask you a bunch of things about it. So the very first thing that you need to do on this kind of analysis is convert all the concentrations. So you get the concentrations here in parts per million, and what you want to do is convert them to mill equivalent per liter. So if you remember the formula for that, the formula, it looks like this. So the mill equivalent per liter equals the milligrams per liter divided by the equivalent weight. So for calcium, so let's see if I can squeeze this in. For calcium, that's basically you're taking 29 and divided by 20. And you're going to get 1.45 for calcium. I've done that for all of the other samples there. You can see I've done magnesium, which is 16.4 divided by 12.2. Sodium is 23 divided by 23, which equals 1, and so on. So I've done that for all of the ions. So on a test, I always advise that you show at least one sample calculation. You don't need to show them all to me, but one sample calculation to show me that you're doing the right thing. And hopefully that all works out, and that will be a mark probably for the sample calculation and a mark for all of the right numbers. So after that, we can add them all up. So all the cations, you can see right here, they all add up to 4.24, and all the anions, they add up to 4.06. So that balancing error formula, remember, it looks something like this. And so basically, I'm going to take take 4.24 minus 4.06. So that's the cations minus the anions, and then the total cations plus anions are 4.24 plus 4.06. We're going to multiply that value by 100, and we're going to get 2.2%. So that's pretty good. So here's another example of these mill-equivalent bar graphs. In class, I did it on the board. I will talk about how I'm doing it here. Usually relatively straightforward. So here's the ion analysis. You can see I've thrown it in this table here to make everything easy. So just like before, what I'm going to do is take 94, divide it by 20, and that will give me 4.7. I'm going to do that for all of the other ions and get all the values here. So usually when I do this, I'll for the tests, I'll hand out rulers, and you can take a ruler and you should declare what your scale is. So I recommend on a piece of paper that your scale is 1 centimeter is equivalent to 1 milliequivalent per liter. So that means for this calcium, so I think I have some labels on here. There we go. So for the calcium, you're going to measure this out. I forgot to put zeros over here. You're going to measure 4.7 centimeters. So this is my calcium right here. The magnesium is another 1.97 centimeters. So I'm going to measure out a second bar like that. And when you add 4.7 plus 1.97, you get 6.7. And then lastly, you add in the sodium, which is another 0.61 centimeters. And your total is going to be 7.3. And if you want to put the units on here, of course, the units are milliequivalent per liter. Going to do the same thing for the anions. So you can see there's the bicarbonate right there. There's the sulfate. And there's the chloride. So there's a couple more marks on the test. So I won't ask you to do any of the fancy graphs, but something like this is fine. I may do the other way around. I may give you a graph and ask you questions about it. And sometimes I do one on the test, and then I might do the other type of question on the final exam. So like I said, one thing you can do is match up the ion pairs. So you can see I've done them all here. There's calcium, calcium bicarbonate, calcium sulfate, calcium chloride. Doing the same for magnesium, magnesium carbonate, magnesium sulfate, magnesium chloride. And for sodium, sodium bicarbonate, sodium sulfate, and sodium chloride. So I finished today's lecture on just introducing the concept of water hardness. So water hardness is, of course, due to multivalent metallic cations. So what does that mean? It means something with a positive charge that is greater than 1. In reality, this usually, almost every single time I've ever seen it, has to do with calcium and magnesium. Sometimes there are other ions around, so iron and manganese are pretty common, but usually they're in such small amounts that when you calculate it out, it's insignificant. It's like, the 4th decimal place or something like that in terms of the actual quantities. Not saying that they're not important in some samples, it's just I've never seen them being significant. It's always calcium and magnesium that are the most important from what I've seen. So what is the big deal about hardness? There's taste, which is one thing. It turns out that apparently water that's completely soft, so has no calcium, magnesium, apparently it's really flavorless. Water that's too hard may have a bit of a taste. And hard water, the most significant issue is scaling. So you can see here in these diagrams, you might have scaling on your faucets or your sinks. You can see there's all this scaling around the edge of the tap, and kind of makes a little bit of a mess. You can clean that off with a little bit of vinegar water, by the way. The big deal with scaling is that sometimes it builds up in pipes. So most houses, it takes decades, but eventually there will probably be a water break, and that's because you get this scaling and buildup in the pipes, and eventually it gets narrower and narrower, and eventually they break. Other issues with hardness is apparently it stops soap from lathering. So if your water's really hard, you may have to use extra shampoo to get kind of all those good suds in there. So if you take a look, here's a chart of water hardness. So Fort McMurray, it seems to me when I measured in the lab, it was about 280 milligrams per liter calcium carbonate. And so that means that Fort McMurray water is very hard. And actually that's really typical in Canada. We have lots of limestone. And because of all that limestone, our water ends up being really hard. Not really any significant health effects. Some water is much, much harder than that. It just means there might be a little bit more scaling in our pipes and a little bit more cleanup in the bathroom. What else was going to say about water hardness? So you probably know that calcium carbonate is, of course, limestones, and that's a big part of the geology of Alberta and Canada in general, which is why there's so much around here. So this is where I'm going to end for today. I will talk about these units next day, about why water hardness is actually measured in milligrams per liter calcium carbonate. I know there's supposed to be magnesium, but these are the units. There's historical reasons that we're stuck with those units, and we'll discuss that a little bit more next day. So see you on Wednesday.